Okay, good evening, everyone. This is going to be a special short tutorial session, although I have named it tutorial number 12 of this course. And I'm Jaya Krishna Sinavkar, a TA for the NPTEL course in various and calculus with applications in control theory and mechanics. So today we'll be reviewing just some of the topics through solved examples. First, we'll start with solving some problems with holonomic and non-holonomic constraints. Then we'll be discussing about variable boundary points, and then finally with Hamiltonian formulation. So let's start with the first question. So it says that uh, given a functional I is equal to T1 to T2 of the uh, uh, T y dot y double dot subject to fixed and conditions, we have to pose this problem as one with non-holonomic constraint. At first, you know very well that you know very well that non-holonomic constraints are those constraints where the constraints contain the derivatives of the of the independent variables, which in this case happen to be, or sorry, or the derivatives of the extremizers, if I call that, yeah. So that's what a non-holonomic constraint here implies. Okay, so we with right now the problem, the functional here is doesn't have any what you call constraints. So we'll artificially introduce a constraint. So let's take z is equal to y star. Okay, so then this implies that z dot is equal to y double dot, right? So what we can do is now we can convert the functional t1 to t2 of f of t, y, z, and z dot dt. This is the new functional. Okay, and mind you that before we had so before what we had is we had a functional in y, right? Y is equal to t1 to t2 of f of t, y dot, and y double dot dt. Now this has become an extremization problem of optimization problem in y and z, and this is subject to a constraint, subject to a constraint gy y dot z dot is equal to y dot minus z is equal to 0. Fine. Okay, so now what you see is now our problem is now constrained optimization, constraint uh, of variational constraint variational optimization problem, right? Variational optimization problem. Okay, so what we do is now let's construct what you call an augmented integrand of the functional. Okay, or what we can say is let's construct an augmented functional, and this will be given by some say j of y comma z, and it's yeah, j of y comma z is equal to t1 to t2 and is equal to f of t. I'll just write f here, denoting that it implies some function in minus lambda of t into g. This is over t, fine. So that we have included a constant here as well. So let's call this integrand here as h. So here h is equal to f minus lambda into, and mind you that I'll write the complete expression here. So f is a function of t, y, z and z dot minus lambda is a function of t, and g here is y dot minus z. Fine. Now what we'll do is now we'll just find the Euler-Lagrange equations. Let us obtain the Euler-Lagrange equations as, so we'll have a set of two Euler-Lagrange equations, right? The first one is d by dt of parcel of parcel h by parcel. So here actually we have actually three terms, right? We have three independent variables. Sorry, yeah, we'll have y, z, and one Euler-Lagrange even for lambda. So this is first will be say y minus 0, right? And the second one is next. And okay, and so this implies that d by dt of parcel h by parcel y dot is nothing but, so you know that f here is independent of y dot, right? So we'll have minus lambda, isn't it? And then minus with respect to y is, so only the f contains y, so f with respect to y is equal to 0. So this comes out to be lambda dot plus parcel f versus 0 equal to 0. And the second Euler-Lagrange equation is d by dt of parcel h by parcel of z dot minus parcel h by parcel. This implies that d by dt of parcel z dot is, now here f is also a function of that, so I can have parcel f by parcel z dot, and the second term doesn't contain f, I mean z dot, so okay. Then minus of parcel h with respect to z. So okay, the first term contains, so I'll have parcel f by parcel z. Then the second one also has, so this will just be plus lambda t, right? Plus lambda of t, and this is equal to 0. Fine. And the third Euler-Lagrange equation is parcel d by dt of parcel h by lambda dot minus parcel h by lambda is equal to 0. Now you clearly see that h here is independent of lambda dot, right? So which means that lambda dot this term is 0. So all we are left with is y minus y dot minus z is equal to 0. Fine. So these are our three Euler-Lagrange equations. Okay, now you'll ask that, okay, how is it related to the previous Euler-Lagrange equation, isn't it? So you can clearly see that, you can clearly see from here that, let me name this equation 1, 2, and 3. So ideally initially the function was in terms of y, t, y, y double dot, y dot, and y double dot. So extremizers of this would satisfy the Euler-Poisson equation. But now what you can see here is we'll have a set of three equations. So, and if we eliminate, let's eliminate lambda throughout. So what you can see here is from equation 1, we have lambda dot is equal to minus del phi by partial f by partial y, isn't it? And then y dot is equal to z, fine. So what we can do is let's make the substitution from equation 2. Differentiating equation 2 with respect to t gives what? And now we can also make a substitution, say z is equal to y dot, so z dot is y double dot, fine. And then minus b by dt of partial f by partial y dot again, and then minus lambda, right? So minus lambda dot. And you can clearly see that this implies that minus lambda dot is equal to partial f by partial y, is it not? So, and then this will just be plus partial f by partial y. And you see that this is the well-known Euler-Poisson equation, right? Euler-Poisson equation. Okay. Now let's go to the next problem. So the next problem here says that the next problem here says that minimize or find the extremal. Okay, find the extremal of I is equal to 0 to 1 of half y prime squared plus y prime plus y prime plus y, where n values of y are free. Fine. Now you can see that in this case, the extremizers, in this case, what you see is, although the endpoints, so 0 and 1 are fixed, but note the conditions at the ends. Okay. So what we'll have is, so the Euler-Lagrange, so the necessary conditions for the extremization of such functional will be, we'll have our Euler-Lagrange equation, which you can clearly see that it's d by dx of del f by, and here f is this RF, and minus del f by del y is equal to 0. And also we'll have this term called partial f by partial y prime. Okay, this will be at x is equal to 1 is 0. Okay. Okay, now let's find our Lagrange equation. See, these are also boundary conditions for our problem. So this means that d by dx of partial f of partial y prime is y prime plus y, okay, and plus 1, fine, and then minus of y prime, and then plus 1 equal to 0. And after this, what you have is y double prime plus y prime, okay, minus y prime, minus 1 is equal to 0, and then you clearly have y prime is minus 1 is equal to 0, is it not? And we can also write it as y prime is equal to 1. So this means that upon integrating it twice, then we'll integrate it. So y prime is equal to, say, x plus a, and then then y is equal to x squared by 2 ax plus b. Okay. Okay, so let's invoke our end conditions here, or the boundary condition. So del f by del y prime, del f by del y prime at x is equal to 0. So del f by del y prime at x is equal to 0. This implies that del f by del y prime is y prime plus y plus 1 at x is equal to 0 is 0. And then this you have is y prime is x plus a. So it is a plus y is y at x is equal to 0, b plus 1 is equal to 0. This is the first condition. The second condition is y prime at x is equal to 1 is equal to 0. Again, in this case, we'll have 1 plus a plus half plus a plus b plus 1 to 0. Okay. And then this implies that 2a plus b plus 5 by 2. Is it not? Or before that, what we see is fine. This is all well and good. Now you see that a plus b plus 1 is equal to 0. And even in this case, we find that we can clearly see that a plus b plus 1 is equal to 0. So all you are left with is this implies that a is equal to minus 3 by 2. Now substituting here gives us a minus 3 by 2 plus b plus 1 is equal to 0. So this implies that b is equal to half, is it not? So therefore our extremizer is y is equal to x squared by 2 minus 3 by 2x plus half. Okay. Now let's go to the third problem in this sequence. The third problem is consider the functional j of xy is equal to t0 to t1 of root over x dot squared plus y dot squared where x and y are functional are functions of the independent variable t. Use transversality condition to find the curve which has the shortest path from the origin to the line y is equal to from the origin. Okay, so mind you that's origin to the line y is equal to minus 2 minus x. Okay, the first thing we can do here is I think there are multiple ways of solving. There are at least two ways of solving this problem. So what we can do is that it says that are functions of the independent variable t, right? So okay, fine. Let's do one thing. Let's take it to be f function f here. Now here there is a problem where the function the functional consists of two dependent variables which are x and y and one independent variable t. So our Euler-Lagrange equation will be a system of two equations. And the first equation is d by dt of partial f with respect to x dot minus partial f by x is equal to 0. And then this implies that d by dt of x is nothing but x dot by root over x dot square plus y dot square is equal to 0. Is it not? So this implies that x dot plus root over x dot square plus y dot square is equal to some constant c1. Call the equation 1, and likewise let's have a second Euler-Lagrange equation which is minus f by y is equal to 0, and this also leads to Similar equation, x dot square plus y dot square is equal to C2, and there is equation 2. Now what you see is divide 2 by 1 to get what? To get y dot by x dot is equal to dy by dt by dx by dt is equal to dy by dx is equal to C2 by C1, right? And this let's call it as m. And upon solving this, we'll have y is equal to mx plus c. And c here is a constant. Again, another constant. And even m is also a constant, right? Now what we see here is, okay, so we have two constants and just one what do you call one bond. I mean, so to speak, the boundary conditions. So in a sense that we are given the originating point. So the origin here is a fixed point, and for the other case, what we have is something like this. Yeah, x plus y is equal to -2, right? This is our line equation. Y is equal to -2 minus x. So this we are given 0, 0, but we need to determine this point. So let's use the fixed and condition. Fixed and condition is uh, y of 0 is equal to 0, right? So this means that 0 is equal to c, is it not? So we have found one condition. Now let's use, since the other point is able to, the other end is able, can freely take any point on the line, which is y is equal to -2 minus x. So we need to have something. So which means the other end point is free. So we need to invoke the transversality condition. Transversality condition. Okay. So the transversality condition, what does it give us? So the transversality condition says that, let's have two quantity first. P is equal to del f, del y, say in this case. Mm, so the transversality condition says that summation of k is equal to 1 to 2 pk del qk minus h del t at t1 is equal to 0. And this for our case simplifies to p1 del x plus p2 del y minus h del t is equal to 0, right? Okay, so then this implies that p1 is equal to partial f with respect to x dot, is it not? And this is nothing but x dot divided by root over x dot squared plus y dot squared. And likewise, p2 is equal to partial f by partial y dot is equal to x dot, y dot divided by x dot squared plus y dot square. And h here is nothing but summation of pi or pk qk, pk delta qk dot, like I don't know, let's call it pk qk dot is equal to 1 to 2 minus of f. And this comes out to be x dot square divided by root over x dot square plus y dot square and plus of y dot square divided by x dot square plus y dot square minus of root over x dot square plus y dot square. And from the first two, addition gives us identically 0, right? Yeah. So effectively, what we have from the transversality condition is that now, so this part will be come here as P1 delta x. So P1 is x dot by root over x dot square plus y dot square into del x. Okay. And now mind you that this del x is the curve. So like I had drawn in the previous page slide, it was, this is our, what do you call, here on this lies our, or in a sense that our x at the tip are allowed to vary. T1 are only allowed to vary on these points, right? Or along this line. So plus y dot plus divided by root of x squared plus y dot square to del y is equal to 0. Is it not? And this happens to be at T1. Okay. And notice is the denominator on both the sides are always greater than 0. Okay. And this has to be the case, is it not? So which means that we are left with is del x plus y dot del y at T1 is equal to 0. Okay. So let's do one thing. So we know that we have a constraint. The endpoint x1, y1 of the shortest length, or so to speak, of the extremizer, the extremal x of t, y of t is allowed to vary along minus x, sorry, y is equal to minus 2 minus x, right? So which means the variations are related as del y is equal to minus del x, is it not? So let's substitute this on in the previous equation. So x dot into del of x plus y dot into minus del of x at T1 is equal to 0. So this leads us to x dot minus y dot at del x T1 is equal to 0. And mind you that the variations can be arbitrary. So this means that x dot minus y dot at T1 is equal to 0, since delta x T1 is arbitrary. So this simply implies that, what does this imply? This implies that our x dot minus x dot 1 minus m x dot at 1, so to speak, let me just call it at T1 equal to 0. Now this implies that again 1 minus m x dot T1 is equal to, again you see that for this to happen for any arbitrary x dot, this implies that 1 is equal to. So therefore, the shortest path is y is equal to 5. Okay, now let's solve another problem. So this problem says that consider general functionals. Okay. It says that consider general functionals of the form I is equal to 0 to x1, k of xy e to the power tan inverse y dot y prime into root over 1 plus y prime squared, where kappa xy is not equal to 0. Right? And desired extremals are subject to the endpoint conditions that x0 and y0 is prescribed and fixed, but x1, y1 is only constrained to lie on the curve. Find the transversality condition that applies at x1, y1. Fine, okay. So we have this expression here. So this is our f, f, right? Okay. So at first, let's find our, so the solution, what I'll say is uh, I'll just write the solution process. So first we'll have our Euler-Lagrange equation, and which is d by dx of partial f by partial y prime minus partial f by partial y is equal to 0. And okay, now what we do is let's have d by dx partial f by partial y prime is, this is somewhat complicated, so let's do it individually. So partial f by partial y prime is equal to, and we need to use this chain rule. So into e to the power tan inverse y prime into 1 by root over 1 plus y prime square into 1 plus y prime square plus k of xy into tan inverse y prime into, this comes to be y prime, right? 1 plus y prime squared. Okay, this cancels out. Fine. So which means that our Euler-Lagrange is given as d by dx of kappa xy into tan inverse y y prime, and then into 1 plus y prime divided by root over 1 plus y prime squared. Fine. Minus kappa xy. Here what we'll have is we'll have e to the power tan inverse y prime root over 1 plus y prime squared into is equal to 0, is it not? Okay. Fine. Okay, now what we do is okay, I have the things I write till now. Let's just check. So this implies that tan inverse y prime, fine, into dy. Okay, fine. Okay, this cancels out. Sorry. I think I have committed a mistake here. Sorry. This is root over 1. No, not root. It's just fine. So this cancels out to give us something else. Okay. So this will just come out to be 1 by prime squared, is it not? Fine. Okay, so there's our, okay. Question to learn. I'll just copy this to the next page. Which undefined result is not one of that constant. So then this implies that so we need to solve for y as a function of x. This is an implicit differential equation. Okay, let's go to the next problem. To find the shortest distance in the plane from point A is equal to -5 to the parabola y squared is equal to x. So A is equal to -1, 5, -1 and 5. And the parabola is x is equal to y squared. We need to find the line which connects. So let this be x0, y0. Let this be x1, y1. These are y squared is equal to x. Okay. So solution, let's construct a functional. J is equal to x0 to x0 is equal to 0. This is fixed end. 0 to y as x1 of root over 1 plus y prime squared and dx. Okay. Let's call it our function f. Okay, so the Euler-Lagrange equation is d by d x of del f by del y prime is equal to 0. So in fact, minus del f by del y is equal to 0, but this term is 0, so this implies that del f by del y prime is equal to constant. Del f by del y prime is some constant c, or it's some constant m. So this implies that some constant c1. Then this we have is y prime by root over 1 plus y prime squared is equal to c1. And then having y prime squared is equal to c1 squared and 1 plus y prime squared. So this gives us y prime c1 square minus 1. 1 minus c1 squared is equal to c1 squared, right? So we'll just call y prime is equal to c1 squared by 1 minus c1 squared is 10 to some constant m. Then let's just have it m squared. So we'll just call it that y prime is equal to m. So upon integrating it once more, so you have mx plus c. So m and c are constants. Okay. So let's use our end condition. So the fixed end condition gives us y at -5 is equal to y at -1 is equal to 5. Then place that minus m plus c is equal to 5. Okay, so this means that c is equal to m plus 5. We now need to determine the value of m. So let's invoke the transversality conditions. Before that, what we need is p is equal to del f by del y prime, and this is given as y prime divided by 1 plus, and then h is equal to p y minus f, py prime minus f. And this gives us y prime squared by 1 plus y prime squared minus root over 1 plus y prime squared. And this gives us minus 1 divided by 1 plus y prime squared. So which means we have p into del of x. This lies on the curve phi minus h of del y, sorry, p of del y minus h. This also lies on phi is equal to 0. Okay, and then both at say x1. Okay, now what is in this? There's h delta x. Okay, so what we do is we can write p into del y as d phi, or in this case, it's let's just parameterize it. Okay, so let's just call it as d y by d some t, and or dy by d xi, and minus let's first parameterize. Let's parameterize our. Let us parameterize the curve of x is equal to y square as gamma, or sorry, let's call it as zeta, and zeta squared. Or sorry, it should be zeta squared, comma zeta. So what, which means that we'll just write this as p of, we can just write it as dy by d zeta minus h. This is at again x1 minus h and dx by d xi, but again x1 is equal to 0. So which means that this becomes p is, we can write simply as y prime is nothing but m, right? Okay, so p is m divided by 1 plus m squared, is it not? And then into dy by dx. Dy by dx is 1 minus, and again I will have the same thing here. What we have here is minus h. H is nothing but, again we'll write plus 1 divided by root over 1 plus y m squared into dx by dy is 2 xi. Okay. And then this entire at x1 is equal to 0. Fine. Okay. So what we'll have is we'll divide multiply throughout by 1 root over 1 time. So we have m plus 2 xi. 2 xi, and xi is nothing but xi at x1 is, and mind you that xi represented that y. Okay. So xi1 is nothing but xi at x1 is nothing but y1, and y1 again has to be the same, right? So it is just so if I call that this was xi at 1 x1, and then this xi at x1 is equal to y at x, and this is the same as m into x1 plus c. Is it not? Yes, right? So this means that we have m plus 2 into mx1 plus c is equal to 0. Okay, now from the continuity of points, we have x1, y1 is equal to x and y at x1. Is it not? So this means that y1 here is mx1 plus c is equal to, and y at x1 is nothing but or I can just call it this one way. Or what I can do is let's say that so x1 is x1, x at x1, and this implies that okay, let's do something here. Let's do something here. X is equal to x is equal to let's say that x1 is equal to x squared. And then y is equal to mx is equal to root over x1. Okay, so upon squaring this, what we have here is x1 plus c whole squared is equal to 1. And upon substituting this, mm, m square is equal to x1 is equal to minus this upon substituting it here, what we get is this implies that m square is equal to let's m is equal to minus 2. So minus m by 2 is equal to m into square by 4 m. And then as c was equal to m plus 5, m plus 5. This means that m cubed plus plus 3m by 2 is equal to 0 cube plus m plus okay. X plus plus 20. So therefore m is equal to minus 2 plus minus 3. So this is not valid. Therefore, all we have is m is equal to minus 2 and y is equal to, so c is equal to m plus 5 equal to 3. So y is equal to minus 2x 3. So let's just check whether it passes through the first point, which is minus 5. When we put put minus 1 and then we get y is equal to 5. So it satisfies that condition. So these are extreme measures. Okay, so I think let's stop our tutorial session today here itself. We'll have the last tutorial session tomorrow.